So in the previous two parts, what we have seen is we have just looked at how frequently or like how recently a page is referenced or accessed, right? Now consider the case where, as shown on the slide, so here, this is the heat map of the page references, and here the more dark colored page shows that that page is accessed heavily, and the light colored page is the page that accessed rarely. So given this configuration, let's say we need a page, which page to select? So there are two obvious choices, right? Either page 2 or page 4. Note that page 2 is actually modified by the process. That means process actually has written something into the page 2. Okay. And page 4 process has just read to the page 4 and there were no modifications to the page 4. So what happens if we, let's say, if we select page 2 as the victim page? So in order to replace page 2, we need to write the page back onto the disk, okay, before replacing it. Why? Because it is modified by the process. So in order to ensure that the memory rights are conserved, we need to write the page back onto the disk. Whereas if we select page 4, we don't need to write back because the process did not haven't modified the page since it has bought in the last time. So page 4 has less replacement cost, right? Because we don't need to write the page back to the disk if we select page 4. So based on this, so this is also a thing that we need to consider, or rather any page replacement algorithm to consider is whether the page should be written back or not. Okay. So what we have focused till now is on the page references. However, we never looked at the late page fault latency, rather the delay uh, that the page replacement algorithm encounters when it has to replace a certain page. Okay? And the key observation here is that it is cheaper to pick a clean page, okay, to replace a clean page than a dirty page. Here, dirty page is the page that is modified by the process uh, from uh, from when it is bought into the memory. Okay, and clean pages are not modified by the process, so replacing clean page is just easy because we don't need to write the page back onto the disk. Now the challenge here is how to get this info, how to know that a page is written by a process. Again, we resort to the hardware. So here, similar to the reference bit, there is also another bit in the page table called modified bit or dirty bit. So this bit will be set by the MMU whenever a page is written to. Okay, so whenever process makes a write to certain page, the dirty bit of that page table entry will be set. Okay, whereas reference bit will be set whenever page is either read or written to, right? So if a page is written to, we both set reference bit and also modified bit. Okay, if the page is read, we only set the reference bit. So here, as I mentioned before, uh, page table entry has a bit called dirty bit that indicates whether the page corresponding to this page table entry has been written by the process or not. Now, using this accessed bit and dirty bit, we can intelligently select a page to replace so that the cost of page replacement is also reduced. So this algorithm is called enhanced FIFO. Basically, we can now enhance FIFO with this dirty bit. So here, given two bits for each page, the reference bit and modified bit. So reference bit says whether the page is needed soon by the process, right? If the reference bit is set, that means it's highly likely that the page will be used again by the process. Okay. Whereas modified bit tells uh, whether replacing the page is costly or not. Okay. So as as I've shown in the table. So here, let's say the case when reference bit is 1 and modified bit is 0. This says that the page is highly likely to be needed soon because reference bit is set. However, to replace the page, the cost is less because we don't need to write the page back. Okay. So the gist of this algorithm is we prefer the page, we would like to prefer a page that is highly unlikely to be used and it has low replacement cost. That means when both reference bit and the modified bit or dirty bit are both zero. Okay. However, we give least preference to the page that has both the bits set, which indicates the page will be highly likely to be used and the page has huge cost to be replaced. Okay. So based on these two bits, we can modify FIFO algorithm as follows. So here, when a page fault happens, for each page, we check the two bits. If the bits are both zero, we consider that as the victim and we replace that page. We don't need to write the page back because it's not modified, right? We just take the page, we just replace that page. It's very good. Let's say we did not find that page. We found a page that has bits 0 and 1. Basically, it's not referenced, but it is modified. So we just record that as the first instance. This is the second chance part of the technique. So we just record that instance and and we continue scanning the pages. And if we see a page with which has 1 0 or 1 1, then we just clear the reference bit. We just clear the reference bit, the first bit to be 0. I mean, we do this only if we haven't found any page that has 0 1. Okay. At the end of round 1, if a page which has 0 1 was found, we just take it because that is the page that has slightly higher cost in replacing. However, we are sure that it will not be, we are considerably, like relatively sure that it will not be used later by a process. Right? After round 1, let's say we did not find any page that has 0 1. Okay. Then we just try one more round. So in the next round, it's very likely that we will find a page that has 0 1 because we are clearing the reference bit for all the pages that has 1 0, right? So in the second round, most likely we'll find a page which has uh, which has 0 1 or 0 0. So this is the gist of enhanced FIFO algorithm. So to summarize, in this lecture and the previous lecture, we saw various page replacement algorithms. First, we saw optimal algorithm that gives us a baseline for comparison, and it gives us the upper bound upper bound for the performance of any page replacement algorithm. And we saw FIFO, and another algorithm we didn't actually saw is random. Here the technique is, as the name says, it just randomly pick a page. Okay, here the efficiency of this algorithm, the algorithm is pretty quick. The efficiency of this varies, it's not guaranteed, right? And we saw LRU in the last part, and we saw how we can approximate LRU by maintaining counters. And we saw FIFO, we also saw FIFO with second chance, where we clear the reference bit, where we actually give a page that is referenced a second chance. Okay. And we saw a different way of implementing FIFO with second chance by using clock handle. And finally, we saw enhanced FIFO algorithm where, in addition to the reference bit, we also use the modified bit or dirty bit to select a page that that is that is highly unlikely to be used and also has less cost in replacing the page. Okay, in the next part, we'll look more into effects of page replacement policies such as trashing. Basically, this what happens when page replacement policy goes wrong, or like what happens under very high memory pressure.